Next, we're going to dive into the standard normal distribution. Before we actually talk about that, though, we're also going to talk about something called the uniform distribution and just kind of how these probability distributions are really helpful for us, especially when they're in graph form. So when we talked about creating a probability distribution, we know those probabilities had to add up to 1. So really what that does when you create that graph, it ends up being that the area underneath is 1. So we can actually use a probability graph to determine what probabilities are for specific things. So what I'm going to do is I'm going to work with that example of the number of females in 2 births, and we're going to go ahead and we're going to find each of the areas, and then we're going to go ahead and also add them up. And then that way that'll help us be able to figure out certain probabilities. So we know if I look at the number of females in 2 births, there's a 25% that both are male. There's a 50% chance that there's 1 female, 1 male, and then a 25% chance that both are female. So if I break this into 3 regions called A1, A2, and A3, when I go to find the area A1, remember these are rectangles, so it's the width times the height. And in this case, the width, this goes from 0 to 1, so it's length 1. And then the height in this case is 0.25. So it's 1 times 0.25, and this area is exactly 0.25, which is the same as the probability that there are exactly no females. If I look at the second area, the width of this goes from 1 to 2. So in that case, again, the length of the bottom bar is 1. And then this height is 0.5. So this would be 1 times 0.5, which is 0.5, which again is the probability for having 1 female in 2 births. And then finally, that third area also has a length of 1 and a height of 0.25. So if you multiply those together, you get 0.25. So when I add these 3 areas together, 0.25 plus 0.5 plus 0.25 indeed gives us a total of 1. The reason this is really helpful is because now if I want to know what's the probability of 1 female or less, I'm really just going to utilize those 2 areas that fall into this category. So my probability of 1 female or less is really area 1 plus area 2. So a 25% and a 50% chance means there is a 75% chance of having 1 female or less in 2 births. So this works really nicely with these probability distributions. What we're going to focus on now is jumping into those continuous random variables. So we're no longer going to have discrete, we're instead going to have that possibility of all of the values in between. But the same idea is going to extend. If I know what this graph looks like for the probability distribution, I can find the area underneath that graph up to a certain point, between certain points, and that will give me a probability of some event occurring. So again, the main focus is going to be the standard normal distribution, but we're going to start with the uniform distribution because it's a lot nicer to work with. So a continuous random variable has a uniform distribution if its values are equally spread over the range of possible values. So ultimately what that means, it's the same probability occurring for any given moment, so it creates a rectangular shape. So when you go ahead and you graph a continuous probability distribution, what it creates is something called a density curve. And so that will give you, again, up to a certain point, this area, which is related to that density, is the probability of that event happening. So what I'm going to do is I'm going to look at a specific example so we can actually see what's going on. So during certain time periods at JFK Airport, security checkpoints are uniformly distributed between 0 and 5 minutes. So this would be the graph of that density curve. So what happens is the probability that someone waits exactly 1 minute isn't so easy to kind of calculate, because really you have 1 minute, 1.01 minutes, 1.001 minutes. Any given moment's a little bit weird, but what I can do is say, okay, the probability of waiting up to 2 minutes would then be anything in here. So the discrete doesn't work because there's too many possible values to pick from. So instead we'll end up looking at ranges for continuous random variables. So if this is our given waiting time, we want to figure out what is the enclosed area for this density curve. So in that case, I need to find two things. Because it's a rectangle, I need what is the height and what is the width of this curve. So it doesn't really matter what you call what, but height we usually consider to the sky, and that height is always going to be 0.2. And then the width goes from 0 to 5, so we subtract the two of them. The width of this rectangle is 5. So my area is, we just multiply the two of these together. 0.2 times 5 does indeed give us 1. So that accounts for the 100% probability of waiting between 0 and 5 minutes at JFK. So what we want to do is, utilizing this table, we want to determine that the probability of a randomly selected passenger having a wait time of at least 2 minutes. So again, this is a range of values. I want to wait at least 2 minutes. So 2 is my cutoff point. And what I actually want is, what is this area here? These are people who are waiting at least 2 minutes, but up to 5. So if I can figure out this area, that gives me my probability. So I need to know what is the area A. And in that case, I still do the same thing. I need to do the height times the width, because it's a rectangle. If I look at my height, well, height of it is still the same as the last example. It's 0.2. And then my width, if I'm going from 2 to 5, this distance is going to be 3. It's 5 minus 2 to give me 3. So 0.2 times 3 gives me 0.6, which tells me my probability of waiting at least 2 minutes is 0.6. Okay. So again, not really doing anything different that we aren't used to. It's still representing those probability distributions, but now we're going to be looking at ranges of values. What we want to focus on instead, though, is that standard normal distribution. So we've talked about normal distributions. They're very, very common because humans behave in a very similar manner. There is a standard, which is your mean, and then within so many standard deviations, most people fall. So we're going to talk about first standard normal distributions. So ultimately, there's many different types, but we're going to focus on this. What happens here for a standard normal distribution, if you graph that density graph, it has this overall what we call bell shape. And so you can see within, remember these are going to be standard deviations, within 2 standard deviations, most people fall. So ultimately this graph is bell shaped. Standard normal means the mean is going to be 0. So the mean ends up falling right here in the middle. And our standard deviation is going to be exactly 1. So what this represents on the graph is the mean plus 1 standard deviation. This is the mean minus 1 standard deviation, and so on. What this actually relates to on the bottom are your z-scores. because you'd have the mean, or your number, minus the mean, which is 0, over your standard deviation, which is 1. So really, the value for standard normal distributions on the bottom are just your z-scores. And then when you add all of this area up or find that true area, it's going to end up equaling 1. The problem is with this graph, it's not so clear cut of how you find the area. I still can use the same process. So if I know my z-score is 1.5, this area would tell me my probability of having an output of less than 1.5. And likewise, if I want more, this area would tell me the probability of having a z-score above 2. But I don't have a straight formula for that area, okay? But ultimately, we can apply the same idea about determining probabilities by using these z-scores. So to give you some examples, if I know my z-scores say something over here, then this area to the left of it let's call it A1. This area would be the probability of a z-score, or of the score, being less than z. So say this is 3, then the area would be the probability of having a z-score less than 3. If I want the area bigger than it, let's call this area A2. This area is the probability of the score being bigger than z, or greater. And realistically, the way you could find this area is because their total is 1. You do 1 minus the area to the left. If you want to do area between two numbers, you can. So say this is z1 and say this is z2. Then the area in this shaded region is the probability of having a score between z1 and z2. So again, clearly you cannot calculate these areas. It would be so difficult for you to sit here because it's not a nice shape. So what's going to happen is we're going to use z-tables to find the areas to get the probabilities. And ultimately, I'll scroll down, but you can really just search z-tables up online, have that available while you're doing your homework. These are not numbers that you are expected to know. But ultimately, the value in the z-table is going to give you the area to the left of that z-score, okay? So I'm going to scroll to those two different z-tables first, and then we'll come back up to these notes. So what happens is you're going to have a giant table. What happens here is you have a bunch of negative z-scores first, and then you can see it cuts to 0. And then there's a whole other table for z-scores that are positive as well. Negative means it's to the left of that mean of 0. Positive is to the right. So the way you ultimately read these is this gives you the first 2 digits, and then the value up here gives you the third. So we're only going to go out to 3 numbers, or three digits on a z-score. So that ends up being 2 decimal places because it's the first digit followed by 2 decimals. So what you have here is this gives you 0.00, and then you read to here, 0. This tells you as a z-score of 0.000, 50% of the area is to the left of that z-score, which makes sense because when you have that standard normal distribution, this cuts it directly in half, 50% this way, 50% this way. If I want a z-score of, say, 1.17, scrolling all the way back down, I would have to go to 1.1 and then over to 0.7. And so I go across and I go down, and this tells me the area to the left of 1.17. Let's say you want a z-score of negative 2.35. So I would go and I would look where negative 2.3 is, and then the next digit is 5. So going over and going down, this tells you the area to the left of negative 2.35. When you start getting past negative 3.9, really those areas are microscopic. So we typically end up going out to 4 decimal places. So this one gives you a 5th just as some extra precision. But anything past this on either way, you can assume is 0. So we're going to start by doing an example where we're going to find the indicated z-score. So the graph depicts a standard normal distribution with a mean of 0 and a standard deviation of 1. So I want to figure out what is this number down here. And what it tells me is that 0.9535% of my area is to the left of this z-score. So I need to find the column and row in our chart in the Z table with a value of 0.9535 or as close to it as I can. So again, the numbers on the left represent the first 2 digits. And this represents that 3rd digit, which is really, if I could write what I'm speaking, the 3rd digit, which is the 2nd decimal place. Okay. So if I go ahead and go through my chart, well, this starts out at 0.5. I need to get to 0.95. So really, I got to start looking down here. Here's 0.94. This is where we start with 0.95. And I want something very close to 0.9535. So this is 0.952. And if I look right here, 9535. Fantastic. That is super close to what I want. So I'm going to look to the left to get my first 2 digits. That tells me my z-score is 1.6. And then I look up to get the next decimal place, which is 8. So this indicated z-score is positive 1.68. Okay. So what it tells me is 1.68 is this cutoff. 95.35% of the area is here, and then 1 minus that is remaining over here. So ultimately, the probability of having a z-score less than 1.68 is exactly this 0.9535. And then the probability of having a z-score higher than 1.68 is 1 minus this amount, which gives us 0.4 or 0.0465. So 95.35% of the area is to the left, and then 4.65% is to the right. So the Z table is always going to give you the area to the left of that figure. Let's try another one, but let's make it more complicated. We want to find the indicated Z-score. The graph depicts the standard normal distribution with mean 0 and standard deviation 1. What they tell us this time is the area to the right of this Z-score. But again, my Z table is going to tell me the area to the left of that Z-score. So instead, the area to the left of Z is 1 minus this amount. So if you subtract the 2, this gives you 0.121. So what I want is I need to find this in the Z table. Or as close to it as I can. So if I start out, I need a 1 in that first decimal spot, and that really doesn't happen until around here. Here's my first 1, and I need 1, 2, 1. So if I keep looking over, none of those have 1, 2. Keep looking over, I'm starting to get there. I need 1, 2, 1, which lands me right here. So this is my area that I'm searching for. So that specific Z-score, I first go to the left, and that tells me it's negative 1.1. And then my second decimal spot, third digit, is a 7. So the Z-score is negative 1.17. So the probability of a Z-score less than negative 1.17 is this 0.121, and the probability of a Z-score higher than negative 1.17 is the area that they gave us, okay? So this shows you how to find the Z-score, but again, more frequently, we're gonna be concerned with if I have this Z-score, that tells me how many standard deviations I am from the mean, what percentage of people are less than that, what percentage of people are greater than that, and also if I have two different Z-scores, what percentage are in between. So that last example we're gonna do is really gonna tie all of those pieces together. So assume that a randomly selected subject is given a bone density test. The scores are normally distributed with a mean of 0 and a standard deviation of 1. Because of that, immediately I know this is standard normal distribution. Mean of 0, standard deviation of 1. The first thing we want to answer is we want to find the probability that a given test score is less than negative 0.91, and we're also going to draw a sketch of that region. So I've got that 0 in the center to represent my mean, and I want a test score of negative 0.91. So if I were to consider that, that's somewhere over here to the left, negative 0.91. I want the probability that the test score is less than this. So the area I'm searching for on my density graph is this. So we're gonna look at the Z-score, or we're gonna look at the Z table to figure out what this area is. So if I call this A, we're gonna use the Z table to find the area of A. Okay. And if I go through and do that, I need negative 0.91. So here are my negative values. I gotta go 0.9, which is right down here. And then I need 0.91, so that is that second value. So this is the area to the left of 0.91. And again, I'm going to round to 4 decimals, so 0.1814. So the area to the left of A is 0.1814. So that probability, it's less than negative 0.91, is exactly this area. So this is the probability of someone having a bone density of less than negative 0.91. Okay. Trying a different one, we want to find the probability that a given test score is greater than 0.79. So 0.79 is to the right. So here is that cutoff. And we want them to have a bone density of greater than 0.79. So I am searching for this area. And I need to figure out the area to the right, but my z-score for 0.79 is going to give me to the area to the left. So the area to the left of the z-score is the following. I have to go to my positive values, so I need to go down here, and I need 0.79, so here's my 0.7, and I need to go over to 0.9, which is all the way at the end. So the area to the left would be 0.7852. Back up to my example, the area to the left is 0.7852. So ultimately, my value of A is 1 minus this amount, which gives me 0.2148. So the probability of the test score being greater than 0.79 is 0.2148. Okay. So let's try one more, and this one's going to be the most complicated. We want what's the probability between two values. So between a test score of negative 2.5 and a test score of negative 1. Those are both to the left. So negative 1 is here, negative 2.5 is here, and I want the area in between. So if I think about how to do this, if I find the area corresponding to negative 2.5, it's going to give me this area here. If I look at my z table at negative 1, what that does is it gives me all of the area to the left of negative 1. So if I want the area in between, oh, didn't even do that. I really need to take the area to the left of negative 1, which is all of this, and then I need to remove out this section, so I need to remove the area to the left of negative 2.5. So to kind of put this into words, this area A is really the area left of negative 1 minus the area left of negative 2.5. Okay. So that's exactly finding the z-scores for each of these. The area to the left of negative 1 Well, I go to my chart and I go to -1 and I need -1.0, so it's exactly this. So rounding that is 0.1587. So the area to the left of -1 is 0.1587. Now I need to look at the area to the left of -2.5. So that's right here. I don't have a third digit, it's just 0. So it's exactly this first piece, which is 0.0062. So the area left of -2 is 0.0062. So the area in between is going to be 0.1525 when we subtract them. So the probability of having a test score between -2.5 and -1 is exactly 0.1525. So to kind of just recap what we do with these. When you have a standard normal distribution, which just gives you z-scores at the bottom because your center is 0 and your standard deviation is 1, you can go ahead and use the table to find the area to the left of that z-score. And then that also gives you the probability of having a z-score less than that. So depending on the specific probability you're looking at, you might have to find multiple z-scores. You might have to use the fact that the area adds up to 1, but you're really just going to be subtracting things, most likely, to find the probability you're looking for. So with these, I'd always recommend drawing a picture, even when we get out of standard normal distributions and just talk about normal. Draw a picture, label things, and actually visualize what area are you searching for. The z-tables are always going to give you the area to the left of that number. So you might have to do something funky if you need stuff in between or if you need the area to the right.